Okay, please welcome Dr. Josh Willis. I was planning the science lecture for this year. I had a couple of GCC faculty members tell me, you got to get Josh over here for JPL. He's great. So I'm going to set him up for failure by telling you how wonderful he is. But one of those two faculty members is Laura Tenenbaum, and she had offered to introduce Josh today. So Laura, take it away.
Hi everyone. So I just want to tell you how much of a treat you're in for. And many of the students have told me that they've never actually met a scientist. So by the time you walk out of here today, you'll be able to say, I actually saw a scientist and heard them speak. So that's an excellent opportunity for you guys. Josh is, when I say he's a scientist, he actually takes scientific data and analyzes it and writes scientific papers about it. So he actually does the science himself. He doesn't just talk about it, but he does it. So you're going to get that experience. Many students have also told me that they get their ideas about science and scientists kind of from the stereotype of the movies that science is hard and cold and that scientists are kind of geeky, boring losers. So because you guys are really smart, you've heard this, right? You're laughing. I know, you've heard it. So now you guys get the opportunity to see for yourself, and you can make up your own mind about what a scientist is like, okay? You're going to see one in the flesh. You're smart enough to figure it out. So please welcome Josh Willis.
Thank you very much. All right, how you guys doing? Are you awake?
Yes.
Really? I had this science teacher in high school, and he had this really great thing he would do at the beginning of class. You know, he would stand there really quietly. Wake up! And then he would do that. It really worked too. Did that work? Are you awake now? Okay, good. Okay, so I want to tell you a little bit about global warming and climate change, and a little bit about what I do and why I do it, and why I think one of the most important things that we have to learn, and one of the most important places to look when we're talking about global warming is actually in the oceans. And this gets overlooked because we don't live in the oceans, most of us anyway. And so I just want to give you some idea about why the oceans are important for global warming and climate change and what that means. Okay, so here we go. This is a picture that you guys are all familiar with. And it's more familiar now because everybody has Google Earth, right? And you know that if you pulled this up on Google Earth and you just spun the Earth a little bit around, almost the only thing you could see is the Pacific Ocean, right? The Pacific Ocean. It's 1/3 of the planet is the Pacific Ocean. So just think about that for a second. If 1/3 of the planet is the Pacific Ocean and 2/3 of the whole planet are the oceans, then just logically you would come to the conclusion that if we're changing the climate and if global warming is real, then a lot of it has to be happening in the oceans, right? And so it's not really that big a surprise if you stop and think about it for a minute, but because the oceans are kind of invisible to us, we often forget about them. And so I'm just going to remind you a little bit about the oceans. And one of the reasons why this is important to NASA scientists in particular is because the oceans are so big, the only way you can get a grasp on sort of the entire ocean all together, all at once, is by looking at it from space. And so that's actually what I do. I look at data from satellites that measure different things about the oceans. I'm going to show you some of that data as we go along. All right, global warming. Is it real? Is it real? Or am I just a bully that's trying to beat up a bunch of nerdy kids, right? What I'm going to try and convince you of, first and foremost, is that global warming really is real. It's really happening, and it's really caused by people. And some of the information in here is part of the reason we know that. But it's by no means exhaustive. The reasons that we know people are changing the climate and that global warming is real are manyfold. There are thousands and thousands of pieces of evidence. People have known something about this for more than 100 years. We've been collecting observations for a very long time. And there's really an enormous quantity of data and evidence and science that points to the fact that global warming is real and that it's caused by people, that we, in fact, today are the biggest driver of global climate change on the planet. Okay, so what do I mean when I say global warming? When I talk about global warming, what do you think of when I say global warming?
Just the atmosphere, the air around us is hotter, I guess.
The atmosphere, the air is hotter. Anything else? Sea levels rising. Right, right. So all these things are a part of climate change and global warming. But really, when scientists talk about global warming, they mean something pretty specific. What they're talking about is the average increase in temperature over the last 100 years. No, I know. Thank you. The last 100 years have seen over a degree Fahrenheit of warming in the global mean. That means that the entire surface of the Earth. So think about this as sort of an average, right? You get a grade at the end of a semester that is sort of an average of all the things you did during class throughout the entire year. And to change the average grade that you get at the end of the semester, you have to do a whole lot of things. So maybe you get an A on this homework and you get a C on that test, and somewhere at the end you come out with a B, right? So we're really talking about something that involves, when we say global warming, and we're talking about climate change caused by people, we're talking about really big things that happen to the entire planet. So you got to keep that in mind. So that means when you walk outside and it's hot today or it's cold tomorrow or whatever, that's not necessarily part of global warming. When we're talking about global warming, we're talking about really the average temperature of the entire Earth heating up. So what causes that? Well, before I get to that, this is interesting because we have some measures of how warm the planet's been for the last many thousands, even hundreds of thousands of years. And if you go back in time and you look, here's today, and if we go back in time, then there's sort of, in the last 10,000 years, there's been some warm periods and cold periods, but then you get back to 10 or 20,000 years ago, and there's this huge cliff. Here it's really cold, many degrees colder in the average temperature of the planet than it is today. And this was an ice age. This was during the last, what we call Glacial Maximum. It means that there were 2 miles of ice covering places in North America. Chicago was under ice. Massive parts of the northern American continent were actually buried under a huge sheet of ice. And this changed the entire planet, the entire climate of the planet. So it was a really big deal. So we came out of that ice age, and it took about 10,000 years between the last glacial maximum and when we really started to come into what we call the Holocene, which is this warm period that's been going on for more or less the last 10,000 years. And it's during that warm period that civilization actually developed. So back here, people were pretty much as they are today, but we didn't have cities and highways and cars and iPhones, in part because the climate was just too hostile. It would change rapidly. It was incredibly cold. People were nomadic. And then we warmed into this warm period where it's been actually relatively constant. And if you look at the warm and cold periods in the last 10,000 years, to us, these seem like really big changes. You know, the medieval warm period were when the Vikings were able to begin to colonize Greenland. And in the Little Ice Age, you know, we saw collapse of societies, civilizations around the world, in part due to changes in the climate. So these little ups and downs were sizable, but they're really nothing compared to the difference between an ice age and a warm period, which is where we are now. So when we look into the future, we're looking at warming by many degrees Celsius. And in fact, we're on a trajectory to warm at some of the highest rates that have been predicted over the last 10 or 20 or 30 years. So we're really looking at moving the climate out of this sort of sweet spot where it's been for 10,000 years into an entirely new planet, an entirely new climate. And now, that doesn't mean it's going to be the end of the world, but it means there's going to be some really big changes. So, what's the cause of global warming? Somebody that hasn't seen this talk before. What's the cause of global warming? Anyone? Anyone? Cause of global warming. What causes global warming?
CFCs, some of the chemicals that we...
Some of the chemicals. Actually, the right answer was Democrats. That's the word that's what I was looking for. That was your, okay, good. All right, Uncle Al, we all know him, we all love him. If you haven't seen Al Gore's movie, An Inconvenient Truth, I know it's a few years old now, and some climate scientists will tell you, oh, he got this wrong, and he got that detail wrong, but it's actually pretty much right. He pretty much got the story right. Not everything was right, Nothing's ever all the way right, but it wasn't a bad movie. So I like to kid Uncle Al here, but he's really not the cause of global warming. What's the real cause of global warming? The biggest cause of global warming today is the increase in carbon dioxide that people have put into the atmosphere by burning fossil fuels, by driving cars, turning on the electricity, all the power we generate, the fertilizer we create. A lot of these things all are created by burning fossil fuels. And fossil fuels come from digging up carbon that's been stuck in the ground for millions of years, burning it, and then the carbon gets attached to the oxygen. You get CO2, and that winds up staying in the atmosphere for a very long time, hundreds, and some amount of the carbon you put in the atmosphere today will be there for 1,000 years. So in fact, we've had ice ages come and go. These are ups and downs of ice ages, and when it's cold, there tends to be less carbon in the atmosphere, and when it's warm, there tends to be more carbon in the atmosphere. And so we've had these ups and downs, but nowhere in the last 500,000 years has carbon dioxide in the atmosphere even approached the level it is today, and today it's actually higher than this. It's getting close. In the next decade or two, we'll hit 400 parts per million. So we're really having a huge influence on the makeup of what's in the atmosphere. It's really quite a profound change, and in fact, some records suggest that it's many millions of years since the carbon dioxide has been this high in the atmosphere. So these are really profound planetary changes, and you can't have that big a change in the composition of the atmosphere and expect just nothing to happen. So how do we know that this is going on? One of the primary ways, we didn't have instruments to measure carbon dioxide 10,000, 100,000 years ago, but we do have these records that are built up in places like the glaciers and ice sheets. And this is really neat because if you look, this is a glacier, and what happens is you see these layers. So what happens is every year, snow falls on the glacier, it sits there, and then summer comes around, and it gets a little warmer, and some of it melts. And then more snow, eventually it gets cold again, more snow falls. And so you get these layers of sort of melted and refrozen ice and snow and water, and they actually trap little bits of the atmosphere inside them. And you can actually tell what was in the atmosphere. You can tell how much carbon dioxide was in the atmosphere back hundreds of thousands of years. And you can also tell how warm the atmosphere was because different isotopes of these carbon and other things are taken up at different rates. So you can actually tease out an enormous amount of information about what the past climates were like by looking in ice cores like this. So, even though we didn't have scientists like me wandering around 100,000 years ago, we do know something about the climate back then. All right, so how does global warming work? It turns out that all the important energy that we get for driving the climate, for changing the climate, for setting the climate actually comes from the sun. So the sun gives us a huge amount of energy, and most of it goes right through the atmosphere because sunlight is a form of radiation that is transparent to the atmosphere. So it just goes right through. It goes right through the atmosphere. A little bit of it bounces off clouds and other things, but most of it goes right through and it warms the surface of the Earth. Now, the warm surface of the Earth also sends radiation back up into space. And it does this because anything that's above a temperature of absolute zero actually radiates energy out into space. You can see this if you buy an infrared camera. That's actually what you're measuring. You're measuring the radiation off of people that's being generated by the fact that they're not absolutely frozen, like Laura. I'm just kidding. All right, so so what happens is this energy goes back up into the atmosphere, and then the atmosphere absorbs most of it, actually, a whole lot of it. And that's because the outgoing radiation is sort of a different flavor. It's a different kind of radiation. It's a longer wavelength radiation. So it's not like the sunlight that comes in. It's different. And so it has different interactions with the atmosphere. And when you put more carbon into the atmosphere, you actually wind up trapping more of that heat that's trying to escape back out into space. So if you're trapping more energy, if you're keeping more heat on the planet, the question is, what happens to the heat? Where does it go? Where does the heat from global warming go? And the answer is very interesting. Anybody have any ideas what takes up the most heat? That's exactly right. The oceans. The oceans take up more than 90% of the excess heat that we trap from using greenhouse gases. The greenhouse gases that we put in the atmosphere, they trap extra heat, and almost all of it goes in the ocean. So look, here's the atmosphere up here. This is where we live. This is what we care about, right? This is where our climate is. This is where we get the snow and the hot days and the cold days. Only 2.3% of this extra heat is warming the atmosphere. So that's a big deal. I mean, that means, it's still important because it's going to heat up the atmosphere, but really, almost all the action is in the oceans. And that's true for heat. It's also true for carbon, actually. A lot of the carbon, something like half of the carbon that we put in the atmosphere, gets absorbed by the ocean. And that's kind of a good thing because it means less of it's in the atmosphere, but it's kind of a bad thing because it means if we take carbon out of the atmosphere, then it actually comes back out of the ocean too. So the oceans are really like the flywheels of climate. They're this huge thing that has enormous inertia. It's like if you stand on a dock by a ship, by a cruise liner, you could run at it and you could hit it as hard as you wanted to and it wouldn't move. But if you just lean on it a little bit, you can actually move an enormous ship very slowly. And that's because it has a great amount of inertia. And the oceans are the same way. Once they're taking up this heat and once they're taking up this carbon, it's still there. If you try and get it back out, you have to pull all the heat out that you put in the first place. So we're really not looking into the future at trying to reverse climate change. We really don't have enough technology and enough know-how to undo even what we've already done. So we're in for some climate change. Some of it is definitely going to be there. It's definitely going to happen. All right, so why is this? Why does the ocean take up so much heat? So what we're going to do is, there's a little experiment, and this is a lot of fun, actually. If you take a balloon and you hold a flame to it, a balloon filled with air, what happens? It pops, right? But what happens if you hold a flame to a balloon filled with water? Some of you, I know you know this because you've done it, right? A balloon filled with water actually will not pop because it's so good at taking up the heat that the rubber doesn't have time to melt and it doesn't have time to pop. So we're going to do a little experiment. And who likes Mickey Mouse? Who likes Mickey Mouse? Somebody that likes Mickey Mouse, come up and help me. You got to like Mickey Mouse, though. You going to come up and help me? You want to come up and help me? Come on. Okay. Just because you love Mickey so much, I brought this balloon specially for you. All right, so here's Mickey. And what we're going to do is you're going to kill Mickey right now. Right? But he'll still love you if you go back to Disneyland. Are you ready? All right. Is everybody else ready? Okay, here we go. We're going to pop the balloon. You sure you're ready?
Pop it.
All right, here we go. Oh, my God. Wow, I'm all moist from my own breath. It was stored in the balloon. Okay, thank you very much. Let's give her a round of applause. Thank you. All right, who doesn't like to get wet? I need another volunteer. Anyone? Come on up. Yeah, come on up. All right, so we're going to do this thing. And I promise you that I have done this experiment many, many times. And the balloon absolutely never pops. So I want you to hold on to that. All right? And there's no danger whatsoever that it's going to pop. But just in case, now I want you to hold it up high. Hold it up high, so it's going to make a big mess if it pops, all right? And just in case, I brought this raincoat, okay? All right, here we go. All right, now you got to give me a little space between, I don't want to burn you. And they don't want me to burn you. And I'm sure that OSHA really doesn't want me to burn you. Okay, so here we go. We're gonna put the flame on the water balloon. You guys ready? Yeah. I don't really think you're ready. You ready? Ready. Okay, here we go. All right, so just rotate around a little bit so that everyone, no, you rotate. There we go. I'll promise not to burn you much, often. Can everybody see that? Yeah. You see that the flame is right there on the skin of are your arms getting tired?
No.
Oh, good. Oh, I can keep you here longer then. That's great. You see that over there? So how long could I stand here? Forever. Forever is a very long time. Yeah, I can stand here. How long can you stand here? Forever. All right, give it up. What's your name?
Angela.
Angela, give it up for Angela. All right, thank you. Thank you very much. All right, so what's the point of this nonsense? The point is that water is really, really good at absorbing heat, right? We really could have stood there for hours, and I know that Laura Tenenbaum has done experiments with 20 minutes and Bunsen burners. I think the blowtorch finally did it, though. So if you try this at home, don't use a blowtorch. That's my advice. But this is an interesting fact here, because what we just discovered is that the water is so good at taking up heat that it actually won't even allow the skin of the balloon to melt. All the sort of black stuff you saw in the end was actually just the carbon from the torch itself. So it really is an amazing property of the water on our planet, that it's so good at absorbing heat. And that's the reason that the oceans are really the biggest reservoir, the biggest place for storing heat in terms of climate change and global warming that we have. And they're really, really important. So let's go back to our little diagram of how the energy works, right? We're getting all the energy from the sun. And if over the long run our planet's temperature is not changing, like that 10,000 years where we had a pretty stable climate, the temperature of the Earth didn't change very much. So that means that over that period of time, the amount of energy that we were getting from the sun and the amount that was going back out into space was almost in balance. Because if it wasn't, we'd have to be either heating up or cooling down, right? We got to put the heat somewhere. So when we change the atmosphere by putting carbon dioxide into it, we actually keep some of that heat that was going out, right? Remember from the earlier diagram. So then our happy Earth winds up warming, right? So we're keeping more heat. The Earth has to warm up. But remember, a warmer Earth also sends more radiation back out into space. So eventually, that warmer Earth will create a new balance. So the warmer the atmosphere gets, then the more the energy that the Earth sends back out into space, and eventually these two will line up again and we will have a new stable climate. But the new stable climate happens at a price, right? The Earth warmed up. The temperature increased. And there's really, again, to reverse this, we have to get not only the carbon out of the atmosphere, we have to get the carbon out of the ocean, we have to get the heat back out of the ocean. It's really, really hard to change these processes and turn them around. So keep that in mind. And also, remember, to do this, to get to the warmer world, 90% of the heat is going in the oceans. So just to get here, we had to take up a huge amount of heat. And we had to warm up the oceans. And to warm up the entire ocean from top to bottom would take something like 1,000 years. So the ocean is really setting the time scale over which climate change happens. Because until you warm up the oceans, the atmosphere is sort of going to tend to be slave to whatever the temperature of the ocean is. Because it's just so much heavier and so much more water and contains so much more heat. So this is a long process. Now, most of global warming will happen before this. It doesn't really take 1,000 years for like 90% of the warming to happen. Because what happens is the ocean, you don't have to warm the whole ocean. Because when you warm it from top to bottom, some of the heat just stays at the top because warm water is lighter than cold water. So we don't really have to warm the entire ocean. It doesn't really take 1,000 years for most of the warming to happen. But changes continue to occur, like sea level rise. And other things. These will still continue to occur. Even if we stopped emissions, even if we set the atmosphere to a constant amount of carbon, we would still see changes, especially in the ocean, for 1,000 years. All right, so is global warming real? Well, not everybody thinks so, actually. Even though there's all this data and all this evidence, there's still a pretty big push against this idea that global warming is real. My friend here from the Institute of Deep Denial and Corporate Smile would say, we definitely know two things to be facts. First, the Earth is not warming, and second, it's flat, right? But you don't really need to be a member of the Flat Earth Club to think that global warming is not real. I'll tell you a little story. A few years ago, I wrote a paper where it looked like the oceans had actually cooled down just a little bit. Now, it turned out that this was totally wrong, and I'll be the first to admit that. The oceans did not cool down. We had some data problems, and we eventually got them sorted out, and we published a new paper. But when it happened, when we first reported that the oceans had cooled down, it actually got a huge amount of attention. Folks like Rush Limbaugh talked about it on his radio show, and he said that the oceans, cooling, this just proves that climate scientists don't know what they're doing. It just proves that we have no idea what's happening on the planet. And he said, to overturn the world economy based on the musings of a few idiot leftist scientists is just stupid. And that's what global warming is all about. Now, of course, in the end, we fixed our error. We actually published a correction. We highlighted our own mistake in the scientific literature. Now, Rush didn't talk about our correction on his show, much to your surprise, probably. But my wife actually, as a gift and a little reminder of the whole thing, she had some new business cards printed up for me where the job title is actually Idiot Leftist Scientist. So if anybody wants one, just see me after the talk. Okay, so how do we know it's real? How do we know that global warming is really happening? Now, I'm an oceanographer, and I just told you that the vast majority of the changes are happening in the oceans, right? So let's look at the oceans. What are they doing? In the last 10,000 years, sea level has actually changed very dramatically. Remember, 20,000 years ago, we had an ice age. That means there was a huge amount of ice on the continent of North America. Now, if there was a bunch of ice on the continent of North America, that ice is frozen water, right? So if you have ice on North America that's frozen water, where does that water come from? Come on, wake up, wake up. Where's the water come from? It comes from the oceans, exactly, that's right. So if there was a bunch of ice on land, it means that sea level was lower 20,000 years ago. And in fact, we know that it was about 120 meters lower. That's over 300 feet lower than it is today. And during that period where it warmed up, where the climate changed, where we came out of the last ice age and we landed in this stable Holocene period, then sea level rose because the ice melted and it ran back into the ocean, and the planet warmed up, the ocean warmed up. That causes sea level to rise too, just because the water expands, gets bigger. So we had sea level rise for thousands of years, and in fact it rose very quickly. But then remember, we had a stable climate. For most of the last 10,000 years, the temperature didn't really change very much. And in fact, sea level rise during the last 3,000 or 4,000 years has been almost negligible. It's been very small, a tenth of a millimeter per year. But if we look at the modern record, just for the last 100 years, then sea level's been going up 10 times, almost 10 times that. Actually, today it's more like 3 millimeters per year. So we know that some change is going on in the last 100, 200 years that really hasn't happened any time in the last several thousand. And not just from these data, but lots of other sea level reconstructions and other things, we know that the rate of sea level rise today is faster than at any other time in the last 2,000 years. So the last 100, 150 years are really special. And what's special about the last 100 and 150 years? It's us, right? It's CO2. It's our change in the atmosphere that's really driving this. Now, if we look a little more closely at that last 100 years, we actually have a pretty good record of sea level going back to the 1880s. And if we look at it, sea level's gone up about 8 inches. It's not that big, right? If you're standing on the beach watching the waves roll in. But think about how much water that is. Remember, the oceans cover 2/3 of the planet. And so the fact is that if you raised sea level by 8 inches, you had to add something like 16,000 cubic miles of extra water. It's a huge amount of change in the volume of the oceans, in fact. And if you look carefully at this record, actually, a straight line doesn't actually fit it very well, right? Over here, it's above the straight line. Down here, it's below the straight line. If you break the record up a little bit, the average rate over this period is about 1.8 millimeters per year. But if you break it up, in the first 100 years, it was more like 1 millimeter per year. 100 years ago rather. 50 years ago, it was more like 2. And now we have very accurate records from satellites that show us it's more like 3. So the rate of change is also increasing. So this is really part of global warming. To change the ocean's size by 16,000 cubic miles takes something that involves the entire planet. And that something today is us. So where does NASA fit into all this? Remember I said at the beginning, to really see the whole ocean, you have to look at it from above. You have to look at it via satellite. And one of the things I do is look at data from the satellites called the JASON and originally the TOPEX satellite. And these are satellites that fly 800 miles above the surface of the Earth, and they can measure the accuracy of the height of the ocean with about 1-inch accuracy. They can measure the height of the ocean to this accuracy everywhere they look. And so you average that all together, you can get a very, very accurate measure of how big the oceans are, how much volume they're taking up. And what you see is that in the last 20 years, sea level's been rising at a rate of about 3 millimeters per year. Remember, at the beginning of the 20th century, it was more like 1 millimeter per year, and now it's 3 millimeters per year. So the rate's tripled in the last 100 years, the rate of sea level rise. And there's all kinds of really interesting things in here. If you look, sea level goes up and down every year. Why would it do that? Any ideas? Why would sea level go up and down every year in the average?
Change of seasons?
The change of seasons, exactly. And the seasons, more specifically, what happens is every year water is evaporated out of the oceans. It falls down as rain over land. And then it doesn't immediately go back to the oceans. It takes a while to run back in. And actually, you can see this up and down in the data. So every year, the Amazon basin, the Congo, other places around the world fill up with water, and that water runs back into the oceans. And you can see this back and forth, this exchange between the oceans and the land. But what's bigger? Global sea level rise in the last 20 years dwarfs this exchange between ocean and land. So in terms of sea level rise, this part that's caused by global warming, that's caused by people, actually outweighs this exchange back and forth that Mother Nature has been doing for time out of mind. So we're really, in a lot of ways, this is some of the proof that we are the most powerful influence in our global climate today. We can affect the oceans in this powerful way that in some ways just outweighs what Mother Nature was already doing. And it's kind of interesting if you look right there at the end of the record. So this up and down we can sort of account for that, this back and forth between the land and the oceans. We can take that out. And if we look at it without the seasonal cycle, without the seasonal back and forth, there's actually a drop in the last year. Anybody hear about this? It's interesting. This drop, it's about 0.5 centimeter in global sea level. It's just sea level went down. Why would that happen? Any ideas why that might happen? Go ahead, speak up. This is the part where you can yell out whatever you want. You don't even have to raise your hand. What? Not enough rain, drought. It's actually the opposite problem. In some places it rained so much that the water was held onto the land for longer than normal. And so actually this process of taking water out of the ocean and putting it on land was sort of hypercharged. And it was hypercharged because El Nino, we had a big El Nino in 2010 that translated itself into a big La Nina. And these are changes in the Pacific Ocean, the temperatures and sea level in the Pacific Ocean that have a big, profound effect on the climate and the rainfall all around the planet. And it was so profound in those 2 years, 2010 and 2011, that it caused extra water to build up in places like the Amazon basin. And if you remember, last year there were massive floods in northern Australia. There was a lot of water that got soaked up in Indonesia and Southeast Asia as well. And so this extra water was so big that it actually lowered the level of the oceans for a little while. But of course, we have other data, we have other observations that tell us where the water went. We know mostly it went in these places, and they're in the tropics, right? So they're warm. This water is not going to stay on the land forever. It's eventually going to run back off into the ocean. And when it does, sea level rise will begin again. And if you look carefully, the places where we know we're losing ice, where ice that's been there for millennia is now melting and coming off into the ocean, those places still lost water, like West Antarctica and Greenland. So even though we had this dip, this temporary dip in global sea level, we know the long run, global warming is going to win out. Eventually, sea level is going to rise again. Now, it's not just sea level rise that we can tell the impact of human climate change. If we look at the ice at the top of the world, this is sea ice in the summer in 1979, measured by NASA satellites. And this is sea ice in 2008 in the summer. So you can see the difference, 79, 2008. And it's not just that I picked two wacky years. If you look at how the area of the ice in the summer changes over time, you see this big downward trend. And in 2007, we had actually the deepest minimum, the smallest amount of sea ice in the Arctic for any time in the whole record. And this was actually pretty famous. This year, 2007, we had massive ice loss in the Arctic, and polar bears became kind of a national icon, right? Because the polar bears, they live on the ice and they hunt on the ice in the summertime. So they use this ice as a platform to hunt seals. But the ice actually pulled away from the North American continent, in part because of the wind changes in the Arctic. And the polar bears were really left without very much sea ice. And they became kind of an iconic figure for a top-level predator that's really beginning to feel the effects of climate change. Now, I'm not a biologist. I just want to say that right now. But, in my opinion, the polar bears are probably going to make it through all this. I don't really think they'll go extinct. I mean, they could always just move south and eat Canadians, right? But the point here is not that the polar bears are going extinct. It's that some really top-level predator in a remote area that's been, has less human impact than a lot of other places on the Earth, is really beginning to feel the effects of global warming and climate change. So this is real, and it's really happening to big, important predators on the planet. And what's another big, important predator on the planet? Us, right? So climate change is real, and it's coming. Now, it's not just the sea ice that's shrinking. I showed this a minute. I'm going to skip that one. My little animation, in the interest of time. But we can actually see some of the other ice disappearing from places like Greenland. And this is a really neat set of satellites called GRACE. It's actually two satellites, and they chase each other around the planet. And whenever one goes over something heavy, the pull of gravity causes it to speed up just a little bit. And then when the second one follows, it just catches up a little bit. And so by measuring the distance between these two satellites very, very accurately, you can actually you can infer how heavy the thing is that you're flying over. And if you're flying over Greenland, you can essentially weigh an entire continent from space. It's pretty cool, huh? So if we weigh Greenland, if we put it on the scale, we see that Greenland has been on Jenny Craig. It's losing mass. It's getting smaller. It's shrinking. And the reason it's shrinking is because more ice is melted every year than snow falls in the winter. So we add mass to Greenland in the winter. You can see that actually here because snow falls. So every year you get snowfall, gets cold, stops melting as much, and so Greenland increases. And then in the summertime, the problem is that the summers are so warm that the ice loss is now overpowering the added mass that you get from snowfall in the wintertime. So we can actually measure these things using satellites from space, and we can really begin to see the impacts that humans are having on our global climate. You don't have to go to space, though. In fact, there's glaciers all over the world. I love to go to the ice talks at science meetings because they have the best photographs. And this is one of my favorites. It's of the Muir Glacier in Alaska. And this is a picture from the early 40s, picture from the 2000s. And glaciers all around the world are in retreat. They're all losing more mass, almost all of them, something like 90%, are losing more mass than they're gaining on the long run. And again, this is contributing to global sea level rise. but it's another reminder, it's another indicator that people are having a big impact on the climate. Okay, one more. This is one of my favorite ones. This is a picture of the Larsen B Ice Shelf. Now, an ice shelf is a big floating blanket of ice that sits on the water. Ice flows down out of the mountains, and it covers the water in this big blanket. And this ice shelf, this is a picture of the Larsen B Ice Shelf at the end of January in 2002. And you can see all these little dark dots. These are actually meltwater pools that have collected on the surface and are absorbing more heat from the sun than the sort of white reflective parts around them. So this is what it looked like at the end of January. This is what it looked like March 7th. And here what's happened is the entire ice shelf has just broken into pieces. And all the sort of fuzzy stuff you see in there are icebergs and floating ice and the remnants of this massive ice shelf, which was something like the size of Rhode Island. Now, to me, the interesting thing is not so much that this ice shelf collapsed. What's interesting is that a few years later, some oceanographers went and they drilled a sediment core where the ice shelf used to be, and they found that the ice shelf had been there for 10,000 years, since the end of the last ice age. So the medieval warm period, the little ice age, all these things, all these supposedly large climate shifts that we've had during the last 10,000 years, this ice shelf survived all that. But it wasn't until human-caused climate change came along that this ice shelf finally collapsed and was lost, and will be lost probably for the foreseeable future. So, I mean, this is the only thing older than Hugh Hefner to break up, right, in our lifetimes. So really, these are profound changes that are happening. Now, I think if you can't see global warming, if you're still trying to deny that people are changing the planet's climate, then you really do have your head in the sand. You're just not looking at the data in an objective way. There's so much data, so many observations, so much analysis of those observations, so many predictions of climate change that all fit this picture of human beings driving the climate. And if you're not seeing it, then it's really, I think, because you don't want to see it. Now, a lot of people ask me, so what are we going to do about this, right? And I used to always put this slide up and say, how you vote is as important as planting a tree or driving a Prius. Because, you can change all the light bulbs you want, right? You can put in compact fluorescence and everything you want. But this is a big problem. It took the whole planet to get here, and it's going to take the whole planet to stop it. So, yes, change your light bulbs. Reduce your power consumption. Don't fly so much. But really, the most important thing you can do is tell your elected officials that this is an important problem. Tell them at the voting booth. But you don't have to wait till the voting booth, right? Where do you live? Yeah. Where?
Eagle Rock.
Eagle Rock. Do you know who your congressman is? No. Have you ever written him a letter? No. That's what you got to do. Write your congressman. Look them up. Find out who they are. Tell them that this is important to you. Because really, we're going to have to all come together in a way that we can't by ourselves in order to do anything about this problem. It's too big, and it takes all of us. Little things matter too. I don't want to say that changing light bulbs doesn't matter. Of course, it matters. But we have to tell the people that are driving the boat that they're going in the wrong direction. And that's really the only way to have a big impact on this problem. So I hope one of the things that you kind of get out of this is that in the end, the facts are going to win, But oftentimes, we fight against the facts that we find difficult to accept. As Al Gore said, inconvenient. And this is a normal process. This is what we do. This is kind of how we operate. But we have to learn to eventually get past it and eventually make progress toward the future. Because right now, we're not talking about reversing global warming. We're just talking about moving the goalposts further and further away. Because every time we put another ton of carbon in the atmosphere, most of it's going to be there for all of our lifetimes and all the lifetimes of our children and grandchildren and their grandchildren. So we really have to begin to act now, and we have to kind of begin to act in unison. So my final message to you remember, global warming is real. The evidence is really everywhere. You can't look, if you're really looking for it, you'll see it. It's there. Also, it's happening in the oceans. That's really one of the most important places that we have to look. And it's one that we can't forget about because the oceans are really important to all of our livelihood, even though we don't live there. But last and most of all, you got to talk about this. You guys are the next generation of leaders of the planet. And, you know, I know you guys are going to do great things. And I know you're going to go out and, you know, change the world. But don't wait. You know, start changing it right now. Write your congressman. Tell them that this is important to you. And with that, I'm going to run out of things to say and stop. Thank you.
Question time with Josh in just a minute, so get your questions ready and you be ready as well.
I'm ready.
Also, before we get to question time, I want to give a bit of a plug for next month's talk, which is also on climate change. Our speaker, Dr. Porna Hall, is here. Porna, do you want to say anything about next month's talk?
No, not really, because then in that case I'll be stealing the thunder out of what I'm going to talk.
Okay.
But the basic idea is the continuation of the same ocean-urban aspect. But I want to examine as to why so many people don't believe that global warming is taking place. Of course, today if you go out, not many people will believe. It's a little cold today.
Very good. All right, so questions for Dr. Willis. Who's first?
Yes?
What happens if we just don't do nothing?
What happens if we do nothing? That's the question. Well, you know, the Earth is going to survive at the end of the day. The question is, where are we going to be on it? And you know, the impacts of things like sea level rise are really quite large, and they're kind of hard to fathom. The high-end projections of sea level rise for the next 100 years would cost something like, you know, tens of billions of dollars per year to adapt to. Just to say, I'm going to move this building away from the coast. I'm going to block this one off, you know, just to adapt to them. So the costs are really quite profound. And it's not just financial costs, but there are also human costs. Millions of people live within spitting distance of today's sea level and the sea level rise that we expect in the next 100 years now. And all those people are, in the face of sea level rise, there's two things you can do. Protect or you can retreat. You can build a wall or you can tear down a building. But sea level rise is going to happen. And, you know, it's going to continue. The question is, how fast is it going to continue? If we continue to put CO2 in the atmosphere, and not just put it in the atmosphere, but put more and more quickly and more quickly, then we're going to really look at huge changes in sea level rise, in temperatures, and also soon things like storminess, things like hurricanes, things like rainfall. You know, we live here in Southern California and we forget this is really a desert. It wouldn't support this much farming and this many people unless we took water from Northern California and Colorado and other basins and piped it here. But if you change the distribution of where rain falls, then you really have very profound implications for how many people can live over here, how much wheat and cotton and other things can you grow there. You know, you really are beginning to change. Our civilization is built on the climate that we've had for 10,000 years. So, you know, I'm not going to stand here and tell you that everyone's going to die and, like, you know, billions of people are going to be killed by global warming. But the fact is that we will face really profound challenges if we don't begin to rein in our emissions in the next 100 years. So it's real. I can't tell you, like, how many babies are going to die, but the changes are big. And some of them are in the pipeline. Some of them are going to happen. The question is, how big will we let them get in terms of the future? Other questions?
Yeah. Oh.
You can go.
All right. I need your comments on two issues. Good talk, but one issue on which I want to comment is if sea level is warming up, should we not expect El Nino cycle to become more frequent?
That's a really great question. If the ocean's warming, what's going to happen to El Nino and La Nina? And the fact is, we don't have a good answer for that, because for everything that makes it seem like it should be more El Nino, you can find some other thing that makes it seem like it should be more La Nina. And we don't know which one's going to win out. We just don't know yet. Our understanding of what causes El Nino, there are people who say it'll look like a permanent El Nino. And there are people who say that it'll look like a permanent La Nina. You can find, it's really a scientific debate. It's one of the areas where we really don't have a good answer. There are a lot of things we know. That's one thing that's important to remember about science. There are a lot of things we know. We know humans are changing the climate. We know the temperature of the Earth is getting higher. We know sea level's rising. But some of the details, and especially details about the future, like are we going to have more El Ninos, we really just don't know yet. We have a lot of work to do, I think.
And that brings me to the second issue. Whatever happened to the global conveyor belt?
What happened to the global conveyor belt? Well, the global conveyor belt, just for everyone's information, is a circulation in the ocean. It's a set of currents and a movement of water through the ocean that carries heat in the Atlantic northward. For the whole Atlantic, in both hemispheres. The North Atlantic heat's going north, the South Atlantic heat's going north, the equator heat's going right across the equator, and it dumps that heat in the northern hemisphere. It dumps it back into the atmosphere around Europe and Greenland and other places. And I can report to you that the conveyor belt is just fine right now. Today, it's still there. It's still carrying heat. There are debates about what will happen to it in terms of global warming. We think in the next 100 years it will slow down. It will begin to slow. It will carry less heat. And what that means for the Atlantic is it will actually see a little bit less warming, because if the ocean's not dumping heat in the North Atlantic, then you get a little bit of cooling in the North Atlantic. But chances are the global warming that happens, just the radiative part, will outweigh whatever the conveyor belt does. So you're not going to see a frozen wasteland in Europe because the conveyor belt stops.
I was hoping for little ice age in Europe starting 2014 or so.
It would be nice. It would be nice. There is some work that suggests that changes in the Arctic may actually cause harsher winters in Europe because of the sea ice changes. But those are still also, people are just figuring these things out. So you can see, I said a lot of things with a lot of certainty up here, but I hope you don't get the impression that all the science is done. We still have a lot of work to do about what all this means, and that's why I'm hoping all of you are going to turn into scientists and take my job away from me. Yes?
I wanted to know, I read somewhere that the global temperature has halted in the last 13 years. Is that true? Why would that be? And is that a cause for people to deny the global warming?
That's a great question. Did global warming stop in the last 13 years? The answer is no. The answer is no, it didn't stop. It's still there. The oceans are still gaining heat. The atmosphere is still warming. Now, you have to remember that in terms of global warming, let me go back. Actually, let me just go back and just make this point. Okay, so this goes up to 2010. So if you go back 13 years from 2010, you're in the late 80s, right? So here's temperature in the late 80s, and there it is today. So it's not stopped. Now, if you cut this record up into little pieces, you can find some periods where it's warming faster, and you can find some periods where it's warming slower if you're very selective about which places you start and stop. And there's all kinds of stuff in here. We were talking about El Ninos and La Ninas. A lot of the big ups and downs and bumps and wiggles are El Nino and La Nina. They're related to El Nino and La Nina. But the temperature record is one thing. Remember, this is the surface temperature. This is how warm it is averaged over the whole surface of the Earth. But go back and look at the sea level for the last 20 years. So 13 years ago from right now, right? So is sea level still rising in the last 13 years? So how could global warming have stopped? So the answer is really no. But the answer to your second question is yes. people do make claims like that and use it to try and challenge the science. But when they are, they're really just being kind of narrow focused. They're not showing you the whole picture, because the whole picture tells the same story that I've been telling for the past hour. And you can't not, if you really are honest with the data, you can't not tell that story. That story is there. It's in the data.
Josh, can I ask the next question? It's about this slide.
Okay, sure.
Sorry to interrupt. This question was driving me crazy during the talk, but I didn't ask the question. You talked about the cycle in the blue line being
Yes.
sort of seasonal.
Yes.
But is there a net global season? I always thought like the season in the northern hemisphere was canceled by the season in the southern.
That's a great question. The thing is, the seasons are not symmetric, northern and southern, because of the land.
Oh, the land masses are different.
Most of the land is in the northern hemisphere. You've got Europe and Asia and Russia and everything.
That's all I wanted to know.
And so the differences between northern and southern hemisphere, they don't cancel out, all because of the land, where the land is. She had a burning one. Yes.
Thank you. I had worked on a water conservation study, and so all of this, what's interesting to me is that as sea levels are rising, and then with water conservation, they're talking about programs of desalination and water recycling. That's probably a scientific variable. What kind of impact does that have on the environment or with global warming?
So particularly about desalination, or so desalination is a tough choice. I mean, the thing is that we need more water here than we have. So where are we going to get it? Right now we pump it over the mountains and we move it through aquifers. But we have the ocean. The problem with the ocean is it's salty. So if you want to use the ocean water, you have to take the salt out. And this is a tough question, because desalination has its own set of issues. Usually, to take the salt out of water, it requires a lot of energy. And where do we get our energy? Fossil fuels. So we're not really solving the problem with desalination. We're just kind of moving it somewhere else. And there's other issues as well. There's other environmental impacts of desalination. I'm not an expert on that, but I know that it causes local changes where you're doing it in the ocean, in the ecosystems and things like that. And all those are things you have to worry about. But the other problem here is that as you walk away from the coast, you go uphill. And so if you're taking all this water from sea level and making it fresh, you now have to deliver it to the rest of Southern California. So you have to carry it uphill. And that takes a lot of energy too.
Yeah, because one of the issues was that we're running low on water source, and so there was a big push on that. But my main concern is that's an artificial fix to an artificial problem that we're incurring. So,
Absolutely, there's no silver bullet here. I mean, that's why we need a bunch of you to turn into scientists and engineers so that you can help us fix this. Because it's a complicated problem, and in a lot of things with regards to climate change and global warming, when you fix something over here, you break it over there. And it's always a trade-off. And this is not a bad thing, it's just something we have to be conscious of and aware of, and we have to deal with as part of the problem. But yeah, desalination is an excellent example of that. That you have to be aware that if you're getting your water from over here instead of over there, there's consequences to that too. We have to weigh those. We have to weigh those carefully. Yes.
A couple of questions, Dr. Willis. One, I didn't get why the sunlight can come down through the CO2 but not go back up
Okay.
as well, or in as great a quantity. And then two, I was wondering if you were trying to really figure out if this were true, is there anything we can look at in just our kind of colloquial, like everyday experience here in Glendale? I mean, we don't live by the ocean.
Right.
We wouldn't witness the
Right.
rise in sea level. What could we look at right here just in our everyday experience that we could make a decision?
Right. So the question about the radiation coming through is just the kind of radiation. So sunlight has a different set of wavelengths and frequencies. It's a different kind of radiation. And the atmosphere doesn't interact with it. It's a short wavelength, and the particles in the atmosphere don't feel its effects very much. It just goes through. But the radiation coming up from the Earth is a different wavelength and a different frequency. And it's just the physical and chemical, really the physical and quantum mechanical properties of the CO2 that cause the outgoing radiation to be absorbed. So the,
Sunlight bouncing?
it's not sunlight bouncing. It hits the Earth. The Earth absorbs it and warms, and then the warm Earth radiates its own energy back out into space. And that energy that's going back out into space is a different flavor. It's a different kind of energy. It's long wavelength instead of short wavelength. And the physics of it work out that it interacts with carbon dioxide, and the incoming radiation doesn't very much. The second question about where can you see climate change, that's not an easy question. All the things I've shown you here are kind of global pictures, and that's the easiest place to see it. But there are places if you look carefully, but what you really need is a long record. So if you go back into the records for temperature in Glendale, and you look back at what sort of the average temperature over a year or two is today versus the average temperature over the year or two 50 years ago or 100 years ago, you can begin to see some of these climate change effects. But it's not that you also have other things going on there as well, like just building city also causes warming. So it's not all global warming. So it's actually not, this is one of the hard things about communicating climate science is it's not that easy to find things in your backyard that are affected by global warming and climate change. But it will be soon, and we're beginning to identify those. So it's not easy.
City causes warming?
Building a city causes warming because when you turn forest into pavement, the pavement absorbs more heat. That's it. There was one over there, yes?
Is your slideshow available online?
I can put it on the internet. You can all download it. There's a dozen versions of this in various forms, but I will make sure that this one is available for download for anybody who wants it. All these slides are stolen anyway, so steal them from me and use them like you want. Yes?
Yeah. What part of the world would you say has suffered the most from any negative impact global warming has had regarding marine life? What might be some of those impacts?
Yeah.
And also, is there a bigger culprit in the part of the world that one bigger than the other?
What was the last part?
A bigger culprit.
A bigger.
That's more guilty as far as
Oh, okay. So impacts and guilt. Impacts, yes, you can see the impacts on marine life in the tropics because corals and things that live there are beginning to bleach more. There are also overfishing impacts that as well. But the real place you see the biggest impacts from global warming is in places like the Arctic, where it's cold, where you're shrinking the sea ice very dramatically. The amount of warming that's happened there has been very disproportionately large, and the impacts are really very large in the Arctic. They're probably the largest in the Arctic. As far as guilt, it depends a little bit on how you define it, because the carbon that's in the atmosphere today, remember, we've been putting that in the atmosphere for 150 years. And I think if you add up the carbon that's in the atmosphere today, then you're asking who's been emitting the most over the last 150 years. That's the United States. We had the biggest per capita emissions a few years ago. Well, actually, we still have the biggest per person emissions. China recently surpassed us in terms of its total emissions, but they haven't been doing it for 150 years like we have. So in terms of, if you really want to point the finger, then the United States and the Western world in particular has probably contributed the most to the net amount of CO2 in the atmosphere today, which is the cause of global warming. Other questions? Cameraman in the back, Scott.
On the subject of what we can do about it, you mentioned that we should fly less, but isn't flying a mode of mass transportation?
Yeah, that's a good question. The question was whether or not flying is more efficient. Actually, for most trips, flying in an airplane is the same as if each person on the airplane drove a car the same distance. So in fact, even though you're driving a lot of people, it takes a lot of fuel to get an airplane up in the air, and it's not very efficient. So if you go to places that count your carbon footprint, one of the first things they ask you is how many airline trips do you take, and that's how many miles do you fly, and that's one of the biggest factors. So it's really not efficient. Hopefully we can develop efficient, more fuel-efficient airplanes. That would help. But yeah, it's a big chunk.
We got time for one more question.
Outside overfishing, what effects does global warming have on fisheries around the world?
Global warming and fishing, fisheries, it's an effect because the warmer oceans do change the ecology. And if you're changing things like phytoplankton at the lowest levels, then the higher and higher you go up the food chain, those changes are felt. But really, I think in terms of fishing, overfishing is really huge. Global warming is part of it, but there are places in the East China Sea that are fished, large areas of an entire sea that are fished through once every 3 days. So that's unsustainable in the long run, period, with or without global warming. So overfishing is the real deal. But whatever is happening because of overfishing is probably being exacerbated in most cases by the warmer waters. And not just the warmer waters, the extra carbon in the water, because the carbon makes the water more acidic, and it makes some of the bugs, it makes them have a hard time growing. And so that can also propagate all the way through the food chain. So the oceans really do have the potential to be one of the biggest, sufferers in terms of the ocean ecosystems. The marine biology really is getting hit hard in a lot of directions.
Okay, folks, we have another class coming in, so we have to stop it there. One more time on a hand for Dr. Willis.